So you fire up a brand new, highly anticipated real-time AI generation model. You prompt it for a photorealistic streaming avatar.
Right, and for those first 5 seconds, the output looks completely flawless.
Exactly. The lip sync is perfect, the lighting is gorgeous, but then, like 30 seconds in, the face starts flickering, the background begins to melt into this bizarre geometric sludge.
Yeah, suddenly you're looking at a blurry, jittery mess.
It's the worst. Welcome to AI Paper Slop, where we skip the fluff and get straight into the research you actually need to know. Today, we are unpacking a brand new paper titled OPSDV,
which stands for On-Policy Self-Distillation for Post-Training Few-Step Autoregressive Video Generators.
Yeah, it's a mouthful, but it's fresh work from researchers at Meituan, HKUST, and CityU, and I want to give you the core insight right up front.
Let's hear it.
We know that few-step autoregressive video generators are, well, they're incredible for low-latency tasks, but they suffer from terrible long-horizon degradation, that melting avatar effect we just talked about.
Right, the temporal consistency just falls off a cliff.
Exactly. Well, OPSDV fixes this bottleneck. They do it by using real, minute-long videos to create a clean teacher cache during training. This provides dense, trajectory-level supervision while keeping the student model entirely on policy.
Which is a massive paradigm shift.
It really is. The result is a huge boost in motion dynamics and visual quality for long video rollouts. And the best part? Zero extra inference costs.
That's the dream right there. But to really appreciate the mechanics of what OPSDV achieves, we first have to isolate why this specific bottleneck in real-time video generation is so notoriously difficult to crack.
Right, because offline generation solved this a while ago, didn't it?
Yeah, exactly. Look at the offline video generation landscape. Models like Sora, CogVideoX, or Hunyuan Video, they rely on full window bidirectional denoising.
Which means they process the entire temporal window at once.
Precisely. They allow every single frame to attend to every other frame, past, present, and future. That global attention gives you incredible visual fidelity and temporal coherence.
But the trade-off is massive latency.
Massive.
Yeah.
You have to wait for the entire video to synthesize before you can view even a single second of it. But the industry is heavily shifting toward real-time causal generation.
Right, for things like streaming avatars, interactive gaming environments, embodied world models. You just can't wait.
You literally can't. The next frame must be generated based purely on the past, with viewing latency measured in milliseconds.
And that causal step-by-step generation relies on transformer KV caches. Right?
Yep, the key value caches.
So you generate a chunk of video, write the keys and values of those latent representations into the memory cache, and then move on to the next chunk, conditioning on what you just wrote.
It is highly efficient because you aren't recalculating the past.
But there is a fatal flaw embedded in this process.
There always is.
Right. As that sequence gets longer, the tiny, almost imperceptible errors in those generated chunks get written permanently into the cache.
And the model then generates the next chunk, conditioned on a slightly flawed history.
Exactly. It makes a slightly bigger error, which also goes into the cache. Fast forward 60 chunks, and those micro errors compound exponentially until the structural integrity of the video just totally collapses.
And the current training paradigms hit a hard ceiling when attempting to solve that error accumulation.
Why is that?
Well, to get fast few-step autoregressive models in the first place, developers typically rely on distribution matching distillation, or DMD.
Okay, so you take a slow, powerful, many-step diffusion model and distill its knowledge into an efficient few-step generator.
Right. But the limitation is the supervision data. The target distribution for that distillation usually comes from a short-clip video teacher.
Ah, I see.
A model trained to perfect a 2-second clip fundamentally lacks the temporal context to supervise a minute-long autoregressive trajectory.
Let's ground this with an analogy for a second. Imagine you're driving a car, and every mile you drive, your windshield gets just a little bit muddier.
Okay, I like this.
That mud is the error accumulation building up in your KV cache. Now, your driving instructor, that's the short-clip teacher model, only knows how to drive perfectly around a pristine, highly controlled, quarter-mile test track.
Right, they've never seen mud in their life.
Exactly. They can teach you how to start the car smoothly and take the first few corners brilliantly. But when you are 60 miles down a muddy highway, barely able to see through the glass, and your car starts veering onto the shoulder.
The instructor has absolutely no idea how to tell you to recover.
Right. They have never been in that deeply degraded, muddy, long horizon state themselves.
Because the short clip teacher cannot offer dense corrective targets along a degraded denoising trajectory. It only understands clean, short horizon states.
So to fix this, we need a teacher that actually knows how to navigate the muddy highway.
Exactly. And this brings us to the core contribution of the paper, adapting on-policy self-distillation, or OPSD, to video generation.
Now, I've seen OPSD making waves recently in the LLM space. My understanding is you have a student model generate a response following its own flawed policy.
Right.
Then you use a teacher model to correct it, but you give that teacher privileged in-context information, like hidden reasoning steps or ground truth facts that the student didn't have access to.
That's the exact mechanism, yes.
But adapting that to the continuous high-dimensional space of autoregressive video diffusion, that sounds like a massive leap.
Oh, it is. It requires a fundamental re-architecture of how the model handles memory during training. The researchers use real, minute-long video data to provide that privileged temporal context.
Creating a cleaner teacher distribution directly on top of the student's exact rollout states.
Yes, but the actual execution hinges on what they call cache intervention.
Okay, this is where I want to dig into the mechanics. Because just feeding a long video into a teacher model doesn't magically fix the student's autoregressive drift.
No, it doesn't.
So walk us through exactly what is happening inside the KB caches of both the student and the teacher branches during this training loop.
Sure. So both the student and the teacher start with the same initial real video prefix, usually just the first chunk of the video.
Just to anchor the scene and initialize their respective caches.
Exactly. After that, the student is forced to go entirely on policy. It takes that initial state, generates the next chunk using its fixed four-step diffusion sampler, and writes that slightly flawed generated chunk into its own KV cache.
And then it just keeps going.
Yep. It uses that self-generated, increasingly degraded cache to generate the third chunk and the fourth and so on. The student is living its exact infant's time reality.
It has to drive on the muddy highway, because if the student model never experiences its own compounding errors during training, it will instantly panic and collapse at deployment.
The moment the history isn't perfect, yeah.
Right. But what is the teacher model doing while the student is drifting off the road?
So in parallel, the teacher is evaluated at the exact same noisy, latent states and time steps that the student is currently visiting.
Okay.
But the teacher is granted a superpower via cache intervention. Instead of being forced to use the student's fully degraded history, the teacher's older history in the KV cache is wiped out.
Wiped out and replaced by what?
By the actual real video frames from the ground truth dataset.
Wait, I have to push back here. If you give the teacher branch a perfect ground truth video cache to condition its predictions on, haven't we just fallen back into the classic trap of teacher forcing?
The oracle problem.
Right. We know from years of sequence modeling that if you train a model as an oracle with perfect history, you create massive exposure bias.
Yep.
At deployment, when that perfect history is suddenly gone, the model fails catastrophically. How does this not create a massive mismatch between training and inference?
Well, the researchers anticipated that exact oracle trap. To maintain autoregressive consistency and avoid exposure bias, they do not replace the entire history with real video.
Oh, they don't?
No. The cache intervention operates on a hybrid structure. The teacher replaces the older history with real video, but it is mathematically forced to keep the most recent chunk generated by the student.
Wait, really? So the teacher's memory is essentially a Frankenstein cache?
That's a great way to put it. Let's trace it step by step. Assume the model is currently generating chunk number 7.
Okay, chunk 7.
The student's cache contains chunk 1, which was the real prefix, followed by its own generated progressively degraded chunks 2, 3, 4, 5, and 6.
Totally muddy.
Right. The teacher's cache, on the other hand, contains the real ground truth video for chunks 1 through 5. But for chunk 6, it must use the student's generated, slightly flawed chunk.
Oh, wow. So if we bring the driving analogy back, the instructor is sitting in the passenger seat. They have a pristine, high-definition satellite map of the entire route you took to get here.
That's the clean past history.
Right. But they are forced to look through your muddy windshield to see the immediate 10 feet of road right in front of the car.
Exactly. And that framing highlights the genius of the intervention. It forces the teacher to answer a very specific, highly valuable question.
Which is?
It is not predicting how to continue a perfect, clean video. It is predicting how to recover a flawed trajectory.
Oh, I see.
The teacher looks at the perfect distant past, registers the slightly flawed immediate present handed to it by the student, and outputs the mathematically optimal next step to get the trajectory back on track.
providing dense denoising level corrective targets for the student while still respecting the actual on-policy cache dynamics.
Exactly. It solves the theoretical bottleneck beautifully.
It really does. But putting on my ML engineer's hat for a second, I was looking at the compute requirements for this and just sweating over the activation graph.
Oh, yeah, the memory footprint.
Right. We are talking about minute-long videos. That is roughly 60 chunks with 3 latent frames per chunk. You are running a 4-step diffusion sampler for every single chunk, for both a student and a teacher branch.
It's a lot of math.
Backpropagating through a recurrent sequence of that length usually means unrolling the entire computation graph in memory, retaining 240 massive transformer forward passes just to calculate one gradient update.
Yeah, that sounds like an instant out-of-memory nightmare on any modern cluster.
Literally an instant crash.
And if implemented naively, it would crash. The sequence length would demand terabytes of VRAM. But the researchers introduce algorithm 1 in the paper, which details a highly memory-efficient, truncated backpropagation strategy.
Okay, how does that work?
The crucial insight is how they decouple the optimization of the vector field from the historical path the latent state took to get there.
Meaning they don't backpropagate through time.
Right. They perform the solver transitions, the actual denoising steps that update the noisy latent toward the clean latent, entirely without gradients. Furthermore, the KV cache writes are also performed without gradients.
Wait, if the cache writes and the solver transitions are stop gradient, how is the model actually learning anything?
That's the magic of it.
Doesn't breaking the gradient chain prevent the model from learning how its past mistakes caused its current state?
In a traditional recurrent neural network, breaking that chain would be catastrophic. But we are in a diffusion framework here, specifically flow matching.
Okay.
The model's objective is not to optimize the entire historical path. Its objective is purely to predict the correct vector field, the velocity at a specific noisy state and a specific time step.
Oh, so they just do it step by step.
Exactly. For a given chunk and a given denoising step, they run a forward pass for the student to predict the velocity. They run a forward pass for the teacher to get the target velocity.
And then compute the loss.
Right there. They calculate the mean squared error loss, backpropagate immediately to accumulate the parameter gradients, and then instantly release that entire activation graph from VRAM.
Before stepping the solver to the next denoising state.
Exactly.
So they are accumulating the parameter gradients online, step by step, chunk by chunk, and only stepping the optimizer once at the very end of the 60-chunk rollout.
That's right. Mathematically, this online accumulation is perfectly equivalent to backpropagating the summed objective over the whole video.
But the memory savings
Are insane. In terms of memory footprint, you only ever retain one gradient-enabled student forward graph in VRAM at any given microstep.
Wow.
The only tensors that persist across the minute-long rollout are the detached KV caches and the accumulated parameter gradients. This allows them to train on these massive, minute-long context windows on a standard 24 GPU node without hitting O-bear errors.
That is the kind of system-level engineering detail that separates a nice theory from an actually deployable foundation model training recipe.
Completely agree.
Now, you mentioned they are calculating the loss on the velocity. I saw in their ablation study that they explicitly compared matching the velocity versus matching the clean latent, often referred to as X0 matching.
Yes, it was a key finding.
I admit I don't intuitively get why mapping the prediction to X0 ruins the long horizon. Why does the prediction space matter so much here?
It comes down to the flow matching parameterization and how it introduces a time-step-dependent scale.
Okay, break that down for me.
In flow matching, the velocity represents the straight-line trajectory between pure noise and the clean data. If you take your model's predicted velocity and mathematically convert it to predict the clean data state, the X0, that conversion requires dividing by the time-step schedule.
So depending on where you are in the diffusion process, the math naturally inflates or deflates the magnitude of your prediction errors.
Precisely. Calculating a mean squared error in the X0 space effectively places a massive, disproportionate weight on the high noise states early in the denoising process.
And drastically undertrains the low noise refinement states at the end of the diffusion step.
Exactly. And in an autoregressive rollout, those low noise, fine structural details are exactly what keep the video stable over time.
Right, the sharp edges.
If you undertrain the low noise refinement, you lose edge consistency, and those geometric errors compound exponentially in the KV cache.
You know, when I was looking at the visual comparisons in the paper, the difference was wild. There is a specific generation of a train crossing a steel truss bridge surrounded by trees.
I remember that one.
Why did the model trained with X0 matching turn the trees into blurry mush by the 30-second mark?
Because it failed to prioritize the high-frequency structural refinement. As the video progressed, the steel truss of the bridge and the sharp edges of the foliage became progressively smoothed out, turning into a geometric sludge.
But native velocity matching fixed that.
Yes. By using native velocity matching, the model is supervised in its native prediction space equally across all time steps. It doesn't artificially penalize the low-noise states.
As a result, the velocity-matched model perfectly preserved those high-frequency details, the sharp steel beams, the distinct leaves.
All the way through the 60-second rollout.
So velocity matching is structurally necessary for maintaining high-frequency fidelity over long contexts. That makes perfect sense. There is one more training detail that caught my eye, though.
Which one?
The rollout warm-up, which they call the M=7 rule. They completely ignore the first 7 chunks of the generated video when calculating the distillation loss. Why throw away that supervision data?
Well, you have to consider the starting capabilities of the baseline models. The WAN-based autoregressive models used in these experiments were originally trained within a local window of about 7 chunks.
Oh, so the model is already highly capable at that short horizon.
Right. If you start aggressively applying the teacher's corrections on chunk 2 or chunk 3, the student's KV cache hasn't actually had time to degrade yet.
You have to let the windshield get muddy.
Exactly. If you correct the student while it's still driving perfectly on a clean track, it never learns how to recover from a skid.
So the student must autoregressively generate those first 7 chunks, which is about 21 latent frames, and write them to its cache to get the internal state sufficiently dirty.
Yes. It forces the model to enter that out-of-distribution, long-horizon state before the dense distillation kicks in. You only want the teacher correcting the student when the student is actually in the weeds.
Because that degraded state is the exact reality it will face at inference time.
Spot on.
And the experimental setup they used to prove this concept is highly rigorous. They didn't just train their own proprietary model from scratch and claim a subjective victory.
No, they applied OPSDV as a LoRa post-training step on 2 established baseline models, self-forcing and long-lived.
Both of which use the WAN 2.1 text-to-video 1.3 billion parameter backbone. And they are generating full 1-minute videos at 16 frames per second.
Which translates to 180 latent frames across 60 sequential chunks.
Evaluating on both self-forcing and long-lived proves that OPSDV is a general-purpose post-training framework.
Nice, because self-forcing is a standard baseline, but it was primarily trained on short clips.
So if they only showed improvements there, a skeptic could argue the gains just came from the model seeing longer videos during training.
Exactly. But long-live incorporates streaming long tuning, specifically designed for long video synthesis.
Oh, I see.
Showing major quantitative improvements on long-live proves that OPSDV's unique cache intervention strategy provides a fundamentally superior supervision signal compared to standard long video training.
It's also worth noting they gave both baseline models the standard attention sync cache mechanisms for a fair fight.
Right, meaning they keep the first few tokens permanently in memory to stabilize the attention scores over long sequences.
So what do the final V-bench-long benchmark scores look like?
The quantitative wins are extremely consistent across both backbones. OPSDV post-training yields significant improvements in overall quality score, and specifically the dynamic degree.
Meaning you were getting vastly superior motion preservation and visual stability over the entire 60-second horizon?
Exactly.
I do see a slight drop in the semantic score in the tables, though. It is just a fraction of a point, but it's consistent. Why does improving the motion degrade the semantic alignment?
The authors note this is a natural trade-off inherent to video generation metrics. Semantic score often measures how conservatively the model adheres to the exact text prompt, frame by frame.
Oh, so if a model generates a highly active dynamic video where the camera pans heavily, perspective shift, the scene evolves.
It often scores slightly lower on rigid semantic matching compared to a model that just generates a mostly static, safe image that barely moves.
That makes sense. The massive boost in dynamic degree tells us the model is taking risks, generating real temporal evolution rather than freezing up to protect its text alignment score.
And the human evaluators clearly prefer the active motion. They ran a user study where participants compared video pairs, judging overall preference, motion quality, and visual quality.
The results are a blowout, right?
Completely. OPSDV was preferred over the base models in 66% of overall judgments. But when you exclude the ties, the cases where humans felt the videos were of equal quality, that preference jumps to a massive 82.5%.
82.5%, that's huge.
And it is heavily driven by the motion quality. Users overwhelmingly noted that the OPSDV videos lacked the jitter, discontinuity, and late-stage blur that normally plague causal autoregressive models.
If you are listening to this and sweating over what this means for your production compute costs, here is the absolute best part of the paper.
Oh, this is the kicker.
We just spent all this time diving into teacher models, hybrid real video cache interventions, and memory-efficient truncated backpropagation. But at inference time?
At inference time, when you are actually deploying this model to run a streaming avatar or a real-time game engine, the extra computational cost is zero.
Absolutely zero extra FLOPs.
Because it is entirely a post-training refinement.
Yeah.
Once the LoRa weights are trained, you completely discard the teacher branch.
You discard the real video cache construction logic, too.
Yep. The student model goes into deployment using the exact same four-step diffusion sampler and the exact same standard KV cache updates it always used.
You get all of this long horizon stability, the sharp, high-frequency details, the coherent motion over 60 seconds without adding a single millisecond of latency to your production pipeline.
It's remarkable. By forcing the model to learn how to recover from its own cumulative errors using privileged temporal context, OPSDV fundamentally raises the ceiling on what causal autoregressive video can do.
It really does.
And, if we step back and connect this underlying mechanism to the broader AI landscape, it raises a really provocative question.
I'm intrigued. What are you thinking?
Think about embodied AI and autonomous robotic control.
Oh, okay.
We know that robotic world models suffer from the exact same fundamental issue, hallucination drift.
Oh, sure. As a robot takes actions sequentially based on its own predicted state of the world, tiny spatial errors compound.
Exactly. Eventually, the robot's internal memory of the room completely diverges from physical reality, leading to a catastrophic failure where it reaches for an object that just isn't there.
Like, the robot thinks the coffee cup is 3 inches to the left of where it actually is because of error accumulation in its internal state space.
Right. So what happens if we apply the OPSDV cache intervention principle to robotic control?
Oh, wow. What if we continuously self-correct agent world models during training by deliberately injecting ground truth memory into a flawed on-policy trajectory?
Exactly. If occasionally swapping an agent's remembered states with true sensory context teaches a video model how to recover from visual blur.
Could that same principle teach a robot how to recover from hallucination drift and reorient itself in physical space?
It suggests that the key to long-horizon autonomy isn't just building better predictive models. It's teaching those models how to gracefully recover when their internal state inevitably gets messy.
That is a fascinating thought to leave on. The future of autonomous models might rely entirely on teaching them how to steer out of a skid when the windshield is covered in mud.
I think so.
Well, thanks for tuning in to this deep dive on AI paper slop. We'll catch you next time with more of the research you need to know. Keep your KV caches clean out there.